Hello students. So today in this video we are going to discuss the next module. We are going to discuss next module, module 4. So we are starting module 4. What is module 4? Work, energy, and power. Okay, so first here we are going to start the concept of work. What is the concept of work? Concept of work done by a force. What is work done by a force? So let us say that there is a body. Okay, let us consider that there is a body, and this body is acted upon by a force. Okay, this is a block you can take, and right now let us not consider friction. So to keep things simple, let us consider that there is a force acting in this direction. This is a force acting, and the ground, there may be friction also, but right now we have to consider work done by this force. Okay, and let's say that with horizontal, this is force is making angle theta. And what is going to happen? This body, let us say, slides. It comes here. Right? After some time, you will see that this block comes here. There is some displacement is happening, and let us say this body is going to displace from this point to this point. So this is the displacement, right? Which in general you can write as delta r vector, because it's a vector. Force is also a vector. Okay. And this is the angle, theta is the angle between force and displacement vector, right? So work done is defined as the dot product of force and displacement. Okay, here force is constant. If force is constant, we can apply this concept. If force is variable, then it is of course integration of f dot dr vector. In this case, when force is not constant, when force is variable. Here important point to note is that the point of application, this is the point, right now the object is like a point object. The point of application of the force is moving, isn't it? So force is applied at this point, or this object you can say. And here this is the displacement that is happening. So this is what is delta r vector. You want here also you can write, isn't it? That is delta r vector. This is force. So if force is constant, we can go with this formula. If force is not constant, we can go with this formula. Okay. Now let's understand little bit details about, like, assume that the force is constant. Now dot product, work done is dot product of force and displacement. What does that dot product means? Dot product means this force, magnitude of force, magnitude of displacement, and cos theta. So here work done can also become 0. Work done can also become positive. Work done can also become negative. In different cases it can be. So let's understand when it can be 0. It can be 0. Assume that there is force and there is displacement. Okay, but still, if let us say theta is equal to 90 degree. So if theta is 90, cos 90 0, so work done is 0. Work done is positive when theta is acute angle, and work done can be negative when theta is obtuse angle. Okay, that's the case. And also if you say that the body is displacing in the same direction and force is also acting in the same direction, let us say this is the force and let us say this is the displacement, delta r. So theta becomes 0 degree. So work done simple becomes force into displacement, isn't it? That is what generally in lower grades they teach, right? But actually it's the dot product of force and displacement, because this is a vector quantity, right? Of course, work is scalar quantity, right? Because dot product is a scalar quantity. And what will happen if displacement is in this direction and force is in this direction? So in that case, angle is 180 degree, 180 degree. So in that case, we can say work done will be written as minus f into displacement, isn't it? Because cos 180 degree is minus 1. Okay, now let us understand some more critical examples. So if you take some examples, through examples we'll understand. So first example is work done by tension. Work done by tension force. Tension force. So suppose if there is a string and through this string a body is attached, let us say there is a ball or an object is attached and this object is moving across this. Let us say it is going like in a circular path, right? So what is the work done by the tension? What is the work done by the tension? So even though there may be change of speed, let us say here speed is v1, here speed is v2, right? Different speed it is going. It has rotated some angle theta. Now here tension will be varying. Let us say at this point you are studying, so tension is acting like this, right? Mg is acting downward, and here if you see this is the same angle theta. You can resolve the forces along the radius direction. Let's say this direction will become mg cos theta and this direction will become mg sin theta, that we know, right? So idea is that there will be a net force towards the center. We have studied that. So there is a net force towards the center which is called centripetal force. So here tension minus, because center is this, so tension minus mg cos theta, that will be the centripetal force, right? Centripetal force. Centripetal force, and we all know centripetal force formula mv squared by r. Here v square and r is the radius. So from here tension we can calculate. Tension is going to be mg cos theta plus mv squared by r. Okay, so of course this speed will also change and angle will also change. So tension is a variable. Tension is not a constant force. Tension is variable. So how do we calculate work done by a variable force? Just now we have understood. So work done by tension is integration of tension into displacement. Now we are taking a small displacement. That displacement of the ball is happening tangentially. Anytime if ball is going like this, we understand that ball is going like a tangential direction displacement. So displacement dx and force is of course along the radius, right? So the angle between force and displacement here theta is going to be 90 degrees. This is not the theta which over a large period of time it is. Okay, here theta we are taking instantaneous. So you can see this is the displacement, right? This is the tension. So anytime, any instant, this angle is 90 degrees. So t dot dx, or let us say this is dr in general. Let's say this is dr. So tension dot dr factor is going to be always 0. Always 0. Okay, this we need to understand. So work done by tension is going to be always 0. Okay. Similarly, work done by normal contact force will also be 0. So suppose if you take a body and let's say if you keep it like this, okay. So normal is always acting like this. Body may displace in this direction. Let's say this is displacement is delta r. Okay, delta r. So again here the angle between them is 90 degree, right? So work done by normal is going to be 0. Okay, that's the concept of work done. Few examples we discussed. Now let us understand next what is energy. What is energy? We will see problems, more problems later, but let us understand energy. So Energy is nothing but it is the capacity to do work. Capacity to do work. And we have various types of energy: kinetic energy, potential energy. Potential energy also, if you consider gravitational potential energy. Then there can be various other forms of potential energy itself. Kinetic energy, all of us know, half mv square. Gravitational potential energy, you know, mgh. Right? That's what it is. So now let's go more into detail. If you write kinetic energy can be also written in terms of momentum. So it is half mv square. You can write it as half m square v square by m. So m square v square is p square, where p is the momentum. Okay, so this formula is important. Kinetic energy can be written as p square by 2m. Okay. Then coming to potential energy actually between two point masses is given by Newton's laws. This distance is r. So potential energy, which is gravitation potential energy, is given as minus g m1 m2 by r. Okay, this is the gravitational potential energy, but approximately while considering the earth as one of the mass and the body kept at some height h from this, right, assuming h is much lesser than the radius of the earth radius is r. So if the distance is very less, okay, this h is very small as compared to r, so the change of potential energy is mgh, and we take the potential energy at the ground to be 0. If you take potential energy ground to be 0 for reference, okay, this is a reference, then potential energy up at any point height, right, gravitation can be approximated as mgh. So this is of course approximation because things may change with height. If you take very large height, even g can change, right? So this is potential energy, kinetic energy. Then let us understand work energy theorem. Work energy theorem, very important theorem. Work energy theorem. What is work energy theorem? Work energy theorem says that the work done by the net force, is equal to change of kinetic energy. Okay, work done by net force. So on a body there can be many forces acting on a body, right? If you take a body, there can be various forces acting on the body. Let us say this is F1, this is F2, this is F3. So many forces are acting, but displacement will certainly happen in a particular direction, right? Displacement will happen in a particular direction. So work done by net force is change of kinetic energy. You may also split that as work done by first force plus work done by second force plus work done by third force, and so on, right? This total work done, that is equal to change of kinetic energy. So initially suppose it was having velocity u and final velocity v. The body will have final velocity, right? Block will be started moving. So in that case we can say that is half m v square minus u square, because final kinetic energy minus initial kinetic energy, that is half m v square minus half m u square. Half m is common, that's what it is. Okay. So this concept of work energy theorem is more important than even conservation of mechanical energy. We will see that also. Okay. So let us say conservation of mechanical energy. Conservation of mechanical energy. Mechanical energy. So first of all, what is mechanical energy? Mechanical energy is the sum of kinetic energy plus potential energy, gravitation potential. This sum is called, right? And assume that there is no loss of energy. Assuming there is no loss of energy due to friction or resistance. If there is no loss happening, that means such kind of forces are not at all present in this. Okay, so if such forces are not present, then we can say that the total energy will remain constant. Total energy means mechanical energy. That means kinetic energy 1 plus potential energy 1 initially is kinetic energy 2 plus potential energy 2. Okay, so that means the change of mechanical energy will be 0. So that means change of kinetic energy plus change of potential energy is going to be 0. So change of kinetic energy is going to be minus change of potential energy, right? Okay, now before we go further, we need to understand what is conservative force and non-conservative force. Conservative force and non-conservative force. So conservative force is that force work done by conservative force. Conservative force does not depend on the path. Okay, does not depend on the path. And work done by conservative force in a loop is equal to 0. Similarly here, work done by non-conservative force depends on the path, and here work done by non-conservative force is not equal to 0 in a loop. Is not equal to 0. Now let's understand more about it. Conservative example we can take here. Any example. Conservative force means you can take spring force, you can take gravitational force, right? Electrostatic force. All these are example of conservative force. Non-conservative force means where there can be loss of energy happens. Example, friction or drag force, etc. So all kind of resistance forces are non-conservative forces. Okay, now let us understand how to identify the conservative and non-conservative force. So suppose if there is a force vector given, which is fx I cap plus fy j cap plus fz k cap. So the curl of force should be 0. Now what is curl? Curl means it is del cross f vector. What is del cross f vector? This is called curl. It should be 0. What is del vector? Del vector is like, what is del vector? We have studied this, right? Del vector is dou by dou x I cap plus dou by dou y j cap plus dou by dou z k cap. This is del vector. So cross product we have to take. So cross product means you take dou by dou x. First of all I j k, right? Then dou by dou x, dou by dou y, and dou by dou z. And this will be fx, fy, fz. You know how to expand this. So you can expand it and it must be equal to 0. Okay, so this thing can also be broken, and further when you expand it, you can say three conditions. What are those three conditions? Suppose you take xy combination. So differentiation of with respect to x, differentiation of x with respect to y. Like this you can do. But this side you have to write force. This side you have to write this force as Fy, this force as Fx. Okay. Similarly, differentiation, let's say yz, dou by dou z. Okay. So this side you should write Fz, and this side you should write Fy. Okay. Similarly, if you want, you can take next. Then next will be xz, right? So here this time this side will be Fz, this will be Fx. So dou means partial differentiation. What is partial differentiation? We can understand by taking one example. Okay, but before we should note that these are the conditions. So if the force is a conservative force, all these three criteria must be valid. Okay, so let us take one example. Suppose force vector is given as x square y I cap plus y square z j cap plus z square x I cap, like this, k cap. Okay, so these are the different component fx, fy, fz. What is this? This is fx, right? What is this? This is fy. What is this? This is fz. So there are three criteria as I told. So let's differentiate partial differentiation x with respect to y must be equal to partial differentiation of y with respect to x. Similarly, second condition as I told, partial differentiation of y with respect to z is equal to partial differentiation of z with respect to y. Similarly, third condition is partial differentiation of x with respect to z must be partial differentiation z with respect to x. Okay, so let's check the first criteria. Here left hand side fx is x square y. See, partial differentiation means when you are doing this fx with respect to y is the only variable. So x square is constant, it will come out, and y differentiation with y is 1. Now let's take this fy with x. Fy, if you take it, is y square into z, right? So you are doing y square z with respect to x. So here there is no term of x. So y square z is a constant here. That differentiation is going to be 0. So of course this is not possible. This is not true, right? It cannot be true because this x square into 1 need not be 0 because x, y, z are variable. Okay. So of course in one case it can be possible when you take origin x is 0. But other cases it is not possible. So this itself is not being satisfied. Similarly, you can check this condition. F of y with respect to z, when you do, y square is constant and z with z is 1. And f of z with z square x, right, which you are going to differentiate with respect to y. So there is no y here. This is coming, 0. It's a constant. This is also not true. Similarly, this one when you do f of x is x square y. With respect to z, nothing is there here, only x and y term is there, so differentiation with respect to z will be 0. Fz with respect to x, z square x, right, with respect to x, so z square is constant, we'll take out, but x with x is 1. So again this is not true. So none of these are true. So this certainly is not a conservative force. This is a non-conservative force. It is non-conservative force. So this is a simple method to detect whether it's a conservative force or non-conservative force, right? So today's session we have discussed up to this much. Then next session we'll go further. Thank you for your attention.